Types of solutions. Solutions may exist as gases, liquid, and solids. Types of solutions include gas solutes in gas solvents, such as oxygen in the air, gas solutes in liquid solvents, such as carbon dioxide in a carbonated drink, liquid solutes in gas solvents, such as water in the air, liquid solutes in liquid solvents, such as alcohol in water, antifreeze, liquid solutes in solid solvents, such as mercury in silver and tin, dental amalgams, solid solutes in liquid solvents, such as salt in water, solid solutes in solid solvents, such as silver in gold. Aqueous solution. An aqueous solution is a solution in which water is the solvent.
When salt dissolves, the polar water molecules pull sodium and chloride ions from the crystal lattice. In fact, an aqueous solution of NaCl contains sodium ions, chloride ions, and water molecules.
Suspensions. A suspension is a mixture in which particles of a material are more or less evenly dispersed throughout a liquid or gas. The particles in a suspension are more than 1,000 times larger than atoms, molecules, and ions. Because of their large size, these particles tend to settle to the bottom of the mixture unless the mixture is constantly stirred or shaken. Colloids. A colloid is a mixture consisting of particles that are suspended in a liquid, a solid, or a gas. The size of these particles is larger than those in solutions, but smaller than those in suspensions. Consequently, the particles are dispersed throughout, but are not heavy enough to settle out. Colloids can be distinguished from true solutions by shining a beam of light through each mixture. The particles in the colloid scatter the light, making the beam visible. Preparation of a solution based on molarity. The preparation of a molar solution requires the following steps. 1. Measure the amount of solute needed based on the desired molarity. 2. Use a small amount of solvent to rinse the solute into the volumetric flask. 3. Thoroughly rinse the solute container and any funnels used for transfer. 4. Agitate the partial solution to get a thorough mixing. 5. Dilute to the mark. 6. Do a final agitation to ensure a homogeneous solution.
To make a solution based on molar concentration, first, calculate the number of moles needed. For 1 liter of a 0.5 molar solution, 1/2 mole is needed. A 0.5 molar solution of copper 2 sulfate pentahydrate requires 124.8 grams of the solute. Some solvent is added to the solute in the beaker, and a funnel is used to pour it into the volumetric flask. Make sure the amount of solvent added is significantly less than the amount measured by the volumetric flask. Rinse the solute container and funnel with several additional portions of solvent, pouring these fluids also into the flask. Again, take care that the solution level stays below the line marking the flask's volume. The flask is stoppered and agitated by swirling until all the solute is dissolved. Remove the stopper and carefully add solvent until the solution reaches the line marking the volume of the flask. This is called diluting to mark. Restopper the flask and agitate the solution with repeated inversion until it is thoroughly mixed. Make sure you invert and revert the flask at least 10 times. The resulting solution will be the calculated molarity of 1/2 molar. Solutes, solvents, and solutions. A solution is a homogeneous mixture of 2 or more substances uniformly spread throughout a single phase. A solute is a substance that dissolves in a solution. A solvent is the substance that dissolves the solute to make a solution.
A solution may appear to be a single substance, but it is actually the result of the mixture of a solvent and 1 or more solutes. Here, the girl is dissolving salt into water to make the solution for a saltwater aquarium. In this example, salt is the solute and water is the solvent. Salt water is a homogeneous mixture containing sodium and chloride ions and water molecules uniformly distributed throughout the solution. This table shows examples of other combinations of solutes and solvents. In each case, the substance with greater volume is designated the solvent. Solutions. A solution is a homogeneous mixture of two or more substances uniformly dispersed throughout a single phase. Although milk may look like a solution, if you look at it under a microscope, you will see round lipid droplets and irregularly shaped protein particles. Milk is a heterogeneous mixture. Salt water, on the other hand, is a solution. The sodium and chloride ions are mixed evenly in the water to form a homogeneous mixture.
Concentration. Concentration is the measure of the amount of solute dissolved in a solvent. It is often measured in grams of solute per milliliter of solvent, or in molarity. A solution's concentration determines some of its properties.
A solution may be described as dilute if it contains little dissolved solute, or concentrated if it contains more solute. Concentration is a measure of a solution's solute content. It is expressed as a ratio of the amount of solute per volume of solution. This ratio may be expressed in many ways, such as grams of solute per milliliter of solution, or as the number of moles of solute per liter of solution. This is called molarity. Fractional distillation in refineries. Fractional distillation is the process of separating components of different boiling points from a liquid mixture by vaporizing the liquid and passing the vapor through a fractionating column. Fractional distillation is a process by which mixtures of compounds with varying boiling points may be separated. A simple distillation setup includes a column which separates the compounds based on their vapor pressure. Take, for example, this mixture of two compounds with different boiling points. When the mixture is heated, the molecules begin to vaporize. They move up the column and recondense. The molecules with the lower boiling points vaporize sooner and move higher in the column. When they recondense at the top, they are collected in a side container. Eventually, all of the lower boiling liquid has left the mixture, and each vessel contains a single component of the mixture. Comparing molarity and molality. Molarity is the number of moles of solute in 1 liter of solution. Molality is the concentration of a solution expressed in moles of solute per kilogram of solvent. The symbol for molarity is a capital M. Molarity expresses the relationship between the volume of the solution and the number of moles of solute. Molarity is often used in calculations involving stoichiometry. The symbol for molality is a lowercase m. Molality expresses the relationship between the mass of the solvent and the number of moles of solute.
Solubility of a solid in a liquid. Solubility is the maximum amount of a solute that can be dissolved in a given solvent at a given temperature and pressure. For solids, it is usually expressed in grams of solvent per 100 milliliters of solvent.
The solubility of a solute is the amount needed to make a saturated solution using the given amount of solvent at a certain temperature. The solubility of sugar in water determines how much of it you can dissolve into this glass of lemonade. Once too much sugar is added, no more can dissolve. It settles on the bottom and the lemonade is said to be saturated. The solubility of most solids in liquid increases as the temperature rises. Therefore, more sugar will dissolve in the lemonade if it is warmer. Factors affecting the rate of dissolution. The following factors increase the rate at which a solute goes into solution: increasing the surface area, agitating, stirring or shaking the solution, heating the solvent. The more opportunities a molecule of solvent has to come in contact with the solute, the faster the solute will dissolve. If the solute is broken down into small chunks, it has a greater surface area and dissolves more readily. In both cases, however, the dissolved first layer has to drift away before the next layer can dissolve. Stirring, shaking, or otherwise agitating the solution further speeds up the dissolving process, sweeping away the dissolved layer and exposing more solute to the solvent. Increasing the temperature increases the speed of the molecules. The faster they move, the faster the solute dissolves. For example, sugar added to hot tea dissolves almost immediately, while sugar in iced tea normally needs a lot of stirring. Pressure, temperature, and solubility of gases. Gas solubility is an equilibrium process that can be affected by temperature and pressure. Gas solubility decreases as temperature increases or pressure decreases. Gas solubility increases as temperature decreases or pressure increases.
The solubility of gases and liquids is an equilibrium process. When gas is present at the surface of a liquid, there is a flow of gas molecules into and out of the liquid. If we increase the pressure of the gas over the liquid, the equilibrium is shifted towards reducing this pressure by increasing the amount of gas dissolved in the liquid. If we decrease the pressure of the gas, such as when we open a new container of soda, the equilibrium is shifted towards reducing the amount of gas dissolved in the liquid. Consequently, the carbon dioxide rapidly fizzes out. On the other hand, if we increase the temperature, the molecules in the liquid have more energy and move faster, making it easier for the gas molecules to escape the solution. If we decrease the temperature, molecules have less energy and move more slowly. If gas molecules are moving slowly enough, they will not be able to overcome the attractive forces of the solution.
Comparing miscible and immiscible liquids. Miscible liquids are solutes and solvents that are able to dissolve freely in one another in any proportion. Immiscible liquids are solutes and solvents that are not soluble in each other. Solutions that are miscible mix or dissolve in one another. Those that are immiscible do not mix. Toluene and water are immiscible. Toluene is highly nonpolar while water is highly polar. When mixed, the two unlike liquids form a definite boundary where the toluene ends and the water begins. This boundary is called an interface. Ethanol and water, on the other hand, are miscible. In any proportions, the ethanol completely dissolves in water. There is no boundary between the liquids.
Like dissolves like. Substances dissolve in substances that are similar to themselves with respect to polarity. Oil and water do not mix. Oil is nonpolar. Water is polar. Water and rubbing alcohol mix. Both are polar. Oil and dry cleaning fluid, tetrachloroethylene, mix. Both are nonpolar.
Hydrogen bonding. Hydrogen bonding is the intermolecular force in which a hydrogen atom that is bonded to a highly electronegative atom is attracted to an unshared pair of electrons in an electronegative atom in a nearby molecule. In a solution of pure water, the hydrogen atoms bonded to an oxygen atom are attracted to a lesser extent to the unshared electron pairs of neighboring oxygen atoms. This attraction between molecules results in a boiling point that is higher than usual. Comparing strong and weak electrolytes. A strong electrolyte is a compound that completely or largely dissociates in an aqueous solution. Solutions with strong electrolytes conduct electricity very well. A weak electrolyte is a compound that dissociates only to a small extent in aqueous solution. Solutions of weak electrolytes do not conduct electricity as well as solutions with strong electrolytes. Electrolytes are categorized by the ability of their solutions to conduct electricity. Aqueous solutions of strong electrolytes conduct electricity readily. Sodium chloride, for example, easily dissociates to form ions in solution, providing charge carriers to conduct electricity. Aqueous solutions of weak electrolytes do not conduct electricity as easily. Notice how the bulb is dimmer when the electricity is passed through the acetic acid solution. Because weak electrolytes do not dissociate completely, there is limited formation of ions. As a result, the solution is a weak conductor. Because no ions are formed in the sucrose solution, sucrose is a non-electrolyte and does not conduct electricity in solution.